Okay, so basically this is our design criterion here. Okay, so zeta is greater than the numbers, zeta omega n equal to that one. So the first step is we will be able to, hopefully, to plot the desired regions for the locations of the poles here. So remember, basically this is the second order systems. Okay, so apparently if we plug in here, this is a second order system. If this is a system higher than second orders, then you can try anyways to approximate it into a second order system. Okay, so for the second order systems, we have then these characteristic equations usually is s squared plus 2 zeta omega ns plus omega n squared equal to 0. This we have this kind of the format. So basically s equal to, so the root s equal to 2a minus b plus minus b squared. Here I do the calculations, minus 4 omega n squared. Okay, so basically here we do the simplification. Basically that's omega n plus minus j and omega n 1 minus theta squared. Okay, so that is the format. And right now I want to see what this means. So basically you can see this is the real part here. Okay, the real part taking this format. So by mapping these informations, and right now we want to see, so this is the complex plane. And right now I simply want to draw the desired regions for this case. So here is the minus 4/3. Okay, so this number much greater than that one, so its real part is this. That means the any point to the left of this line, that is a desired one, right? And furthermore, we check this one, then we check out this one. So zeta greater than 0.07, so what is zeta? And if you remember, this is a complex plane, and this angle is a cosine of zeta. Okay, so here we take this one, a cosine of zeta, and zeta is a cosine of 0.07. This one is 45 degrees. So which means we also have this. So zeta is greater than that, and so that means it is in these regions. Okay, and we take the overlap of the two desired. So basically here, you can see the desired region is in this. Okay, so that is the regions for us to select the K1, K2 such that the pole, the poles or roots of the characteristic equation according to here. If your calculation of K1, K2 such that the root is outside these regions, then you redesign and recalculate the K1, K2. Okay. So again, in this morning, I just activated the homework 7, and the similar way, and you have to. I ask you to draw the desired region such that I can verify. Once you have anything being calculated, you try to draw your calculated roots onto the complex plane to see if they're falling into the regions. If not, then sorry, redo the calculations. Okay, so that is the design thinking. So now with this one ready, and we see what happens. So let me move to this side. So for this case, continue from there. Let me get out the screen. So these characteristic equations for that formula basically is 1 plus g plus gh equal to 0. Then we plug in the numbers there. So 1 plus k1 s plus 2 plus k1 k2 s plus 2 equal to 0. Okay. So here we can do the things. So right now we have two parameters. The first step is let me try multiply all the terms within these kind of denominators. So that becomes s plus 2 plus k1 plus k1 k2 as equal to 0. So here, for example, here for the, let me just redefine this number, this one, let me call this is beta, and let me call this is alpha. So that becomes s squared plus 2s plus beta s plus alpha equal to 0. Okay. So now we have this one, we have two parameters here. And here I'm going to show you is one of the approach you may try. And usually the thinking process is, again, we try to fix one value, and yes.
So you have s squared times s plus 2.
Oh, that should be 3.
Okay.
Thank you. Yes, there's a 2. Thank you. So usually for the multiple parameters, the simplest strategy is this. You fix one value and then you work on the only one, the other one. Okay, for example, if we would fix the alpha value, then basically this one we can use the typical root locus method, and then you determine beta. So based upon a given or based upon guess value of alpha, you can calculate beta. Then with the two value being determined, then you can determine your location, the roots, and plot it. If not falling into the desired range, re-guess the value of the alpha and redo the whole process until reaching the goal. Okay, so you can initially guess alpha or you can initially guess beta, either way. Okay, so now for this one, and right now I will try is, I will, in my noting, I think I will try to start guessing alpha first. Okay, so the strategy is this. And use the root locus method to determine beta. Okay, so that's the strategy. So now for this case, and let me, so in this way, with this one, I want to convert it into the standard form of the root locus, so with the beta as the parameters. So in that case, I will try is this, rewrite everything as 3 plus 2s squared plus alpha. Holy cow, you see my mistake coming from here. I try to multiply every single term by the denominator, so here that should be s, right? Got it? So hopefully, please multiply it. So this should be s, so in this way, this should be square, and this should be s. I think that should be the right one. Sorry about this, okay? So in this way, we rewrite this, and s squared plus 2s plus alpha, and plus beta as equal to 0, and beta, keep in mind, is our parameter, so I divide everything. So right now I try to convert everything into the standard form. Okay, so with this one, basically the role of beta simply is a k we've been familiar with in our root locus plotting, right? So now we're going to guess the value of the alpha, okay? And here the guessing the alpha should be very straightforward. As long as you keep guessing as a positive, non-negative value, then just do it. And usually here you can write a program in MATLAB and keep trying. And so from here, basically the alpha for this case, and we're going to apply the root locus. So basically here, the root locus is applied to this characteristic equations, okay? And if you remember again, if we begin our root locus, so here is our patterns, the QS and PS equal to 0. How we started? For example, 1 plus k, say s plus 1, s plus 1, s plus 2, s plus 3. Okay, so how we started? We started by identifying the zeros of this open loop system, so 0 here, and identify the poles here, minus 2 and minus 3. We start from here, right? So the similar way, this is our open loop systems. We're going to start with identify the things. And now, in this case, here the the poles are determined by this. Okay, so are determined by s squared plus 2s plus alpha equal to 0. And the 0 is at s equal to 0, right? Okay, so in this way, with this information, we can plot. But right now, with this in mind, the alpha representing, when we determine the alpha, the pole location will be changing. So from here, how would you know? The quickly way you can try is this. Okay, you can solve for the poles. Basically, you say, for example, if you really want to solve for it, then you can say the pole is located at, for this case, 2a minus 2b plus minus b squared minus 4ab. So that is this one. Okay. So this value will give you the location of the poles. Okay. Another better way for doing this. So this is the first one. Another way to do this is this. Location of the poles. We simply drop it. We simply try to draw it. Location of the poles can be expressed down here. So the locations of the poles can be visualized like this. So location of the poles basically is determined by s squared plus 2s plus alpha equal to 0. So if we, again, using the root locus method onto here, then once we plot is all the tracking or the collection of the points that allow us to visualize the location of this one. You see? So for this case, you can see 1 plus alpha s squared plus 2s equal to 0. So for this case, let me quickly draw it. And here, 1 minus 2. So what I draw is the possible locations of the poles. And for example, alpha equal to 0 is here. And for any alpha greater than 0, that can be anywhere here. So basically, all the possible value of the poles, doesn't matter how you select the alpha, will be here, nothing else. So here, what I draw is the starting point. Here, the starting point of the root loci for this equation will start from any point here. Won't be anywhere. You see what I mean? Again, we're starting from here. Right now, our goal is to plot the root locus of these characteristic equations such that the roots for certain value of the beta falling into that desired range. Okay, and for this root locus, the root locus will start at these locations. The root locus of our system, we're going to design the root locus is going to start at poles. That means the root locus of this system is going to start anywhere we drawn here. You okay? You got my point? Good. So now we can using the MATLAB and to help us to choose. So let me plot this one on MATLAB and then we can do the curve. So numerators equal to 1. Denominator 1, 2, 0. And system equal to transfer functions.
Is it TR, not TF?
TR.
Well, yeah, you wrote TR.
Transfer function.
Transfer function.
DF.
Isn't the
Oh.
function TF?
Sorry. Okay. So root LCUS. Okay. So right now here we're showing starting point, and so here we can pick alpha. So from here you can see alpha at this point. Right now I move my cursors to here and click it, and here gain, that means alpha, right? So right now we have this one, then we rewrite this one. So basically this one corresponding is 1 plus alpha and 1 squared plus s equal to 0. So gain, that means alpha. Or in terms of our standard, that corresponding is a k value. Good, okay. So, so from here I don't want this one, so let me delete it. And in my choice, I select alpha to be 20. So around here, so let me see. So this is gain is 1.7, so that is small. I want to enlarge this, and so that will be axis. I want to change the scale of this, and from 0 to minus 8, minus 5, minus 5. So this one I'm asking the horizontal axis from 2 to minus 8. The vertical axis dimension is from minus 5 to 5. Oops. Axis. Oh, it's asking from minimum to maximum, so that should be minus 8 and 2 and minimum to maximum, so that should be right. So right now I change the scale from here you can see from 2 to minus 8, from minus 5 to 5, okay? So alpha, in my exercise, I select alpha equal to 20, and that is about here. Okay, 21. So let me move, and I keep pressing the mouse, the right button. I keep pressing, and then I can move the cursors. Okay, so here we can do precise whatever. Okay, so here for my first choice is I select alpha, and I choose alpha equal to 20. So alpha 20 corresponds to the point here. So for that point, basically corresponding s equal to minus 1, minus 1 plus minus j 4.36. So that means this is a point here. So the 2 points are the poles. So right now the poles are at, let me write one here. So the root locus of this system will start from the 2 points, because that is the poles, right? Okay, and the root locus of this system will end up at 0 here. Okay, with this one, so we can begin to move on. So when alpha equal to 20, basically here you can replace alpha equal to 20. So let me rewrite that equations. So for this case, by choosing alpha equal to 20, s squared plus 2s plus 20 equal to 0. Okay, and now we're based upon this, and we can plot the root locus one more time for the different systems. So for this case, I prefer is have a script. And so let me do this again. Right now I'm going to plot the root locus for this one. So here let me say the numerators is 1, 0, and denominators equal to 1 to 20. And 20 is our parameters. I would say alpha. So here, because I want to do kind of parametric, so here ALPHA, I'm kind of putting to the parametric form such that later we can modify quickly. Okay? Okay, so in this way, alpha 1 to alpha. Okay, so unnecessary. Then we can do this system equal to transfer functions. Numerators, denominators, and then root locus system. Okay, so right now once you have this one, you can save it. Okay, you can save it, and let me save it and say save to I would say the exercise 1. Okay. Right now you can see here it's going to save into this path, and if you don't like it, you can save to any personal local place. And let me do it. So let me say if I can find any locations. Okay, I want to save it into ME409. That is the local drive on the desktop. Okay, so whatever I save there. So under these situations, if your location of the file is different from here, then you have to instruct the MATLAB to go to that way. So you're going to change this one. Okay, you're going to change this path to where you stored. Otherwise, the MATLAB won't be able to find it. Or the other option is you add this path into somewhere. But here, the quickest way is here. So let me change it. Oops. No, so I'm going to search for it. Desktop, where's desktop?
Users.
Users. Search for my name.
Yeah.
And desktop and okay, so from here the file is here. So we can execute it. Okay, so I save it, and then right now if you execute it, then this figure is going to overlap, which means going to overlap, going to overwrite. And if you don't like to overwrite, probably here you can add it up is one figure, one figure. In this case, you simply asking MATLAB to open new figure window and then draw the two things separately. Okay, and so here let me do this one, EX1. Okay, so basically that is drawing on the new windows, and let me compare to this. Okay, so right now basically the two plot are at the same scale. The horizontal axis take 10 units, vertically also 10 units. So if you want to compare, basically you can see this point is our starting point here, right? We choose it, so it must be here. So this one will provide you as maybe a checkpoint to see if your calculation is correct. Anyhow, so from here, that is all the possible values for any for the roots for the beta. So the quickest way is on MATLAB, you can simply pick point. Okay, this point, as long as you pick a point that falling into this range, okay, in this range, that's pretty much easy, as long as you keep that angle is less than 45 degrees. And then as long as you keep that real part of that number is less than 1.33, then that is the good point. That is the good location for you to choose. Okay, so from here we can see, you can see the damping ratio. Damping ratio is theta. Theta is 0.862. That is larger than 707. So that is a good option. Then we further check. The pole location, the real part is minus 3.5, 3.85. That is less than our design is minus 1.33. Okay, so that can be the good answer. So in this way, you can answer me, okay, the beta is equal to 5.71. You've done the job. You good? Okay, and given this case, probably we can try to plot the desired regions onto it. So desired regions is 45 degrees, so that is 45 degrees here. And then minus, this one is minus 4/3. So basically, so this one I highlighted is our desired regions here. Good. So basically for that kind of particular homework questions, and basically that's the open questions, and again, probably Scott, we can stop now.